Okay, happy Wednesday. I can't believe how time is moving on. I appreciate you either joining in person or joining later on through a recording to our weekly live online session where we'll have a look of the most important things regarding this week's chapter content and do a little bit of updating in general of what's going on in the course content. So this week represents week 12. So we're making a steady progress through the course. And last week you took your second exam and second practical. So we're really moving to our last bigger of a section of material that we'll be covering. And for the rest of the semester, our focus will be now firmly on the nervous system and looking at various different parts of the nervous system, various aspects of that, and so on. I did want to, at this point, thank you for your amazing work on the exam 2 and practical 2. I can always tell every week the great effort and great attention that goes to the assignments and goes to the coursework, and it's definitely translating also to your testing performance. So this group just keeps amazing me and keeps being wonderful. So thank you so much for everything you're doing. Here is a little bit of a plan for today of things that we'll be talking about. I have a couple of general announcements as well to share with you. And like usual, we'll probably spend most of our time just reviewing the key points of the lecture material. Like I mentioned, we're really making an amazing progress with the coursework. I know sometimes when you're doing these courses online, it's easy to get into the kind of feeling that, oh, weeks just kind of had a little bit of a similar repetition of the materials and types of assignments that are expected. Part of that is by default and by design. I want you to have some predictability so you can plan your week and your timetables and schedules, kind of knowing what to anticipate. But part of it is working for some students. Some students are getting to the routine and really enjoying that. And some students are kind of feeling like, is it being seen, the work and effort that you're putting in? And I want to make sure that you know that it definitely is. You are on a final stretch. We're embarking on our final big set of chapters that we'll cover, like I mentioned, about nervous system. So at this point, you put in so much and so wonderful effort on this course. So please keep up the momentum so we can get you that fantastic final grade that you deserve. Um, like I mentioned earlier on, we will be focusing on the nervous system. Nervous system is going to be divided in multiple different sections over the coming weeks. We'll talk about central nervous system, peripheral nervous system, autonomic nervous system, and then special senses, so sense organs. And then we get to the end of the semester and we'll wrap up this section as well by taking our very last exam of the course. Before I get too far with other material, I did want to mention that I will be posting a little later, either today or tomorrow, an announcement about next week when our college gathers together to celebrate the World's Kindness Day and World's Kindness Week, really. And there is an event taking place on our Williams campus on Wednesday. There'll be events throughout the college through the entire week. I know that there's going to be a big event on Tuesday afternoon at our Pecos campus, where there's going to be a chance to hear from speakers who are experts on this subject matter. So I just wanted to put it out quickly at this point, just as a shout out that that's coming up. I'll try to make also an opportunity for anyone who feels that they would love to join and maybe have a little bit of extra credit that I would be able to offer for participation and so on. So please know that that is going to be showing up on your Canvas course announcements. It absolutely is not required. It's just something that I try to share when there's events going on at the campus, and I think that it's going to be a fun option for you. And we'll see if we can make it worth of extra credit as well. So I should be sharing my other screen now, where you'll see on the Wednesday event taking place at the Williams campus. I believe that there will be some celebration of the Kindness Labyrinth and other things that are taking place. And we will have on both campuses, both at Pecos and Williams, a share table available as well. And this is going to be mainly clothing and clothing related things that people have donated. So no cost, just grabbing what you need, making use of finding a good home for the products. So they will be available for the, I believe, for the week on both campuses, if I'm not mistaken. So I'll share more in the announcements, like I said, about those. I'm not hands-on involved in this, but I think that it's going to be a fun opportunity and something that hopefully many of you will find useful. So with that having been said, we'll just return back to our presentation so that we can move through the weekly material. So let me share my screen once more. And like I said, I'll try to share an announcement as soon as possible. I do have an assignment for my own schooling, big assignment due tonight, so it might not be until tomorrow that I get to this. I've been doing at the beginning of these weekly meetings kind of a little checking based on the work by author called Pueblo on a book called Inwards from Asian background, and I picked at random one thought for us to start with, and the thought says that I closed my eyes to look inward and found a universe waiting to be explored. And when that by random popped up from the pages, I really thought that it was very appropriate for what we're doing today when we're starting our discussion about nervous system as kind of an introduction to nervous system. And how I often introduce the nervous system to my students aligns pretty well with what this quote tells us. And I often tell to my students that this is really all that you are. You are basically your central nervous system and then structures attached to that, including your spinal cord and nerves. Everything else of us is really packaging and casing and support structures. So all the experiences, all the hopes, dreams, planning that you have really happen at the level of the nervous system and at the central nervous system. So I think that that's really kind of nicely bridging us from that thought of the internal world to the system that we'll be looking at in over the several next weeks. Students usually like to know very carefully what's to expect in terms of the homework. This week, homework, all I have for you is a chapter quiz and chapter practice anatomy activity. Both of those, as usual, you'll be completing on Connect, and I'm asking you to send them in by the end of this week, so by the end of the Sunday. And I think that there are good ways of kind of working through the material and checking that you're seeing the highlighted most important elements of the material. So those are going to be available for you on this week's homework assignments. As I speak to my students about nervous system, we all have our own perspective, how we approach it. What I like to do is refer to my previous life, my previous career, where I spent some amount on this field with a couple of curious cases to get us thinking about nervous system and how nervous system is so fascinating. First one is based on a book by Oliver Sacks, and the name of the book is A Man Who Mistook His Wife for a Hat. And this is a collection of case histories that Dr. Sachs shares about. And one of those cases literally is a man who, for certain reasons, through impacts on his nervous system, even though he saw normally, the vision worked normally. When he looked at his wife, what he saw at the perception that took place at the level of the brain was not his wife, it was a hat. And in response to that, then that man tried to put the hat, what he perceived as a hat, on the hat shelf, for example. And obviously that did not go well when the wife opposed to being placed on a hat shelf. So there was really nothing wrong with the senses. There was something actually happening more of on the level of giving interpretations for what that gentleman was sensing. So I think that that's going to be an interesting case to look at. The gentleman actually was a doctor. Often in medical cases, we abbreviate names to secure some privacy. So this Dr. P actually suffered for visual agnosia, where there's an impaired recognition of visually presented objects. So again, nothing wrong with the vision or intelligence, more of to do with the recognition. This was due to occipital lobe damage. I believe that there might have been also some temporal lobe damage, but it really shows how these case histories help us to start to unbundle what different parts of the central nervous system, especially, what functions are associated with them. The second clinical example that I wanted to talk about relates to Phineas Gage, and that's a fairly famous case that you might have heard in your psychology classes, for example. Phineas was an American railroad construction foreman, and at the time when these railroads were being built, one of the steps of kind of eliminating of the material on the way was that they drilled a hole to the rocks and then filled those with the black powder and exploded the rock out of the way. Railroads have to run fairly flat. You can't have steep hills and down, up and down. That's not conductive for the mode of operation that trains provide for us. So when Phineas was working with this black powder, he was using a large iron rod, and that to push the black powder into that hole in the rock, and that caused a spark. And as a result, that large iron rod was driven through his brain and his head and destroyed much of his left frontal lobe. Interestingly, Phineas did not die as a result of this, but lived for, I believe, 12 more years. But the people who knew Phineas before this injury said that his personality and his behavior changed drastically. There's a quote from a friend that says that Phineas was no longer Gage. So really what we're seeing is, again, locating those functions in our central nervous system to certain parts based on the injuries that have taken. So we now know that frontal lobe is, for example, responsible for your personality. So as a result of this injury, Phineas had a significant change on that. In the past, we relied greatly on studying injuries, and then maybe later on, once the person had passed away, looking at the possible brain injury damage, figuring out what's going on there. But really, these days we can do a lot more. We can do brain imaging, and especially functional brain imaging, which allows us to ask the subject to perform certain activities and then take images of the brain at the same time and analyze what's happening with that, so that we can locate these functions within the central nervous system. That really brings us to talk about nervous system at large, and there's going to be two communication systems in your body. And the first one of these communication systems, which is what we're going to kind of wrap up with our semester on BIO201, is the nervous system. Then we will start BIO202 by talking about endocrine system, which is all about hormones. Both of these systems really are responsible for passing messages from one body part to another. How they accomplish this job does differ drastically, and you'll see more of that when we get to the endocrine system. But at this point, we can really think of the nervous system as a way of sending messages from one body part to another. Sometimes these messages are coming from our extremities and passing through our central nervous system, so our brain. Sometimes there are commands that travel from the central nervous system to somewhere else, telling our body to do something in response to those messages. These messages are largely electrical. We call them action potentials that travel within the neurons, so nerve cells. But between different neurons, and also between neurons and, for example, muscles, there we will see the neuromuscular junction, there is also chemical messaging that takes place. These electrical impulses are incredibly quick. We're talking about a couple of milliseconds in duration, and they're incredibly specific. So passing messages from a specific part to another specific part, and creating almost immediate responses for us. With that in mind, we can kind of take a kind of broader view of nervous system. The nervous system really has three overlapping functions. First function that we'll talk about is the sensory input. So we have various different sense organs. We collect information. Often it's converting information from the world around us to these nerve impulses at those sensory organs, and then passing it often to our central nervous system. And then we also have processing information that takes place at the central nervous system. Often we are overwhelmed with the amount of information coming into our central nervous system. We have to do selecting and choosing which of that information is crucial for us, and then process that information, and based on that, formulate then whatever it is that our central nervous system ends up doing, whether giving conscious attention for something, or whether causing then responses in response to that information, or something else. But that's really the integration portion of the nervous system functions. And finally, we have the third function of the central nervous system, which is carrying out acts in response to commands from the central nervous system. So your central nervous system will send out motor output, for example, to muscles, and that will cause then our muscles to move. And often these three steps are all interconnected. So we see something, or we hear something, or we feel something, we process that information, then we respond to that. For example, through motor response. And if we really think about these three steps, they sound very much like our homeostatic feedback mechanism loop that we talked about earlier, don't they? So stimulus and sensing the stimulus with the receptors would fit into the sensory input portion. The integration of information really refers to what was happening at the control center level, with the set point being set there, processing and interpreting information. And finally, the effectors represent now, for example, this motor output. So effectors, for example, muscles, but it could be also glands that then responds based on those signals from the central nervous system. So all of these three parts, even though they're separate three parts, they work very much together most of the time on most of us. Now we can look at the nervous system and divide nervous system into a few different parts, and these parts are what we're going to be using when we tackle the content over the several next weeks. So nervous system can be divided into central nervous system, which really contains your brain and your spinal cord. part. I often describe this to my students as a computing or processing part of the nervous system. And we see that a lot of that is located at the dorsal, so backside of the body, really responsible for integration and control of mechanisms and information. Then we also have a section known as peripheral nervous system. This includes all other parts of the nervous system that don't belong to the central nervous system, so various different kinds of nerves that we'll see, and also the sensory organs. I often think of these and discuss about these with my students as these communication lines, almost like antennas or receivers, and then passing messages, and also passing messages from the central nervous system to those effectors that we just saw. So, like I mentioned, peripheral nervous system is located outside the CNS, outside the central nervous system. This includes your spinal nerves and your cranial nerves, for example, especially. So that's one division method that we often do, and we can divide the peripheral nervous system further into voluntary somatic portion, which is responsible for things like movements and actions, and autonomic or involuntary portion that we don't have a control over. This is mainly unconscious, and the autonomic branch of the peripheral nervous system can be then further subdivided into sympathetic nervous system and parasympathetic nervous system. So we'll have a look of that as well. Here, what I really wanted to show was another way of dividing the nervous system. And what we see here really is the two functions of the sensory function carrying information to the central nervous system, and then the motor function carrying information from central nervous system to those effector organs. So many ways to divide nervous system, and these divisions are what we're really going to be focusing on so that we can chunk this material, the manageable portions per each week that we're going to be working on this material. So what I wanted to do next really was for us to talk a little bit about a specific aspect of the nervous system, and the specific aspect that I think that we should talk about is going to be our division to the sympathetic and parasympathetic branch of our autonomic nervous system. So sympathetic branch is often described as our fight or flight responses. These are responses that literally we produce in response to either fight for our survival or trying to get away from a threatening situation, for example. So many stressful situations would trigger your autonomic nervous system sympathetic branch. Things like excitement, fear, anger, embarrassment. We see physiological changes in response to that. I'm going to mention just few, but for example, your heart rate will go up, your blood pressure will go up. Your respiratory system, especially the bronchi at the airways, they will dilate so that more air can get into our lungs, so we have resources. Digestive system is depressed. We're not really worried about extracting energy and nutrients from the food if we're fighting for our survival or escaping the situation. Blood vessels will dilate as well, so that the more blood can flow into, for example, the muscles that we need either for that fighting or flighting the danger. Sympathetic nervous system was described there, but let's compare that to parasympathetic nervous system. And parasympathetic nervous system is something that I talk to my students about when we think of how are we feeling after our Thanksgiving meal. So this is often described as a rest and digest system. Your pupils will start to constrict, your heart rate and blood pressure go down. Your digestive system starts working harder. Also, salivation goes up. Urine and feces production also go up. Your respiratory system, your constrictions end up constricting. So it's really this relaxing state where we're focusing on body's maintenance mechanisms. We're focusing on doing those things like digesting and getting rid of materials that we don't want to have in our body, for example, with urinary system removing excess hydrogen. So we see that those are kind of two ways of looking at the autonomic nervous system. What I really wanted to do next was to show you um, neuron. And what we're seeing here, we're seeing um, typical neuron, and I wanted to go through it and highlight the different parts of a nerve cell. I think that that's going to be a rather useful activity for us. So we'll spend a little bit of time on that. I'm just checking whether this shows up elsewhere, and I don't think that it will show up elsewhere. So this is a good time for us to discuss about it now. Let's look at what we see when we talk about nerve cells. And there's many different kinds of nerve cells. So what we typically teach you is just a very general kind of a combination of most important characteristics of nerve cells. They don't really exist in this form or shape as such, but it's a good way to summarize various different nerve cells' common characteristics. So just like any other cells, nerve cells will have a cell portion, cell body portion, where we find cytoplasm, and we also find a nucleus within this cell body. So that's something that we're already familiar with. And like I said, we're seeing that cell body there as well. That cell body is filled with cytoplasm, and those were important for functions that we saw there for maintenance of the cell, all those important roles that we associate there. Like I shared, nucleus, not only does it house the genetic material, nucleus also within this cell and cell body of a neuron is responsible for coordinating functions of this cell. So we see a lot of that, a lot of kind of keeping us organized. We might need to weigh in some information that's coming in and leaving the neuron and choose really what do we react on, what's worthwhile for that. So that brings us to talk about how does the information come to the cell body within the neuron. Well, neurons have these kind of expanding portions. We call these dendrites. You can think of these dendrites almost like little antennas. This is how cell is collecting, the nerve cell neuron is collecting information from around it. So they're responsible for receiving that information. Let's see if I can get this to work without too much interference. And the number of dendrites can really vary. Some neurons have many, some have less, but what's common is that these dendrites, like I said, are collecting information from around the nerve cell and passing that information then to the cell body so that we can process it and choose what we want to do on that information. Often these dendrites also reach out a little bit from the cell body, so we're covering some ground in terms of collecting that information. And again, let me tidy up this picture. For some reason, I'm getting a little bit of interference there. So now that the cell has received the information and it's probably done some processing, choosing what information is worthwhile to react to and what is not, there's going to be really a long, it can be longer on some, it can be shorter on some, but but this axon portion that comes out from the cell body. And this is the portion that really transmits the message onwards within and from the nerve cell. So we collected all that information with the dendrites to the cell body. And now we process that information, and that information can only propagate to one direction, and one direction only, along the axon. And obviously axons are a little bit more complex, but one analog that many of my students like to use is that they think of it also almost like as an electrical wire. Similarly, as we see in electrical wires, it's the electricity that passes. Those messages within the axon of nerve cell are actually electrical impulses that are then passed onwards. We can sometimes also see what are known as collateral branches from the axon. Not all nerve cells will have those, but sometimes we will see those. So the axon can make branches as well. So that's one way how these nerve cells can actually control that the message gets spread to a little bit broader area or more parts. But like I said, not all nerve cells will have collateral branches, but some of them will. So these branches that come out of the axon. Once we get to the very end of the axon, this can be again varied quite a bit, but often we end up seeing that axons have structures known as axon terminals. So this is where the message is either passed to the next nerve cell, and here we could see, for example, next nerve cells dendrites connecting, or it could be, for example, to a structure that's working like a muscle that we're passing the message to. So these axon terminals are responsible for that process of passing the message to the next structure, whatever the structure is. Nerve cells can form these chain-like mechanisms that message passes from one neuron to the next neuron, and so on and so on. Or it could be that it is really connecting then directly to an effector that we'll see next, like a muscle. But let's label those axon terminals as well. And like I said, the messages within the neuron are going to be electrical impulses that we're seeing traveling. And it is definitely noteworthy to notice that these electrical impulses travel to one direction and one direction only within this axon, as we discussed. But interestingly, now as the message is moving from the axon terminal to the next neuron or next target organ, this message is not going to be electrical message anymore. It's actually going to be a chemical message. So these axon terminals can release chemicals that then pass that message onwards through an area known as synaptic cleft from that's a small gap between the neuron and the next portion. So that message is going to be chemical that we see passing there. At this point, we've seen quite a few parts of a typical neuron. I want to add one more portion here. Sometimes what we do see is that the axon is actually surrounded by these blobs of fat tissue. And these blobs of fat tissue are not just a random thing. They very much have a purpose why they're present there. So they surround the axon. Not all neurons will have these, but some will. And we call these blobs our myelin shells around the axon. There's few things that this myelin can do for us. It can provide us a little bit of insulation, like you would if you think of the electric wire analog, protecting those electrical impulses passing in there so that there's no interference. But in addition to that, this myelin can help us to speed up the propagation of the electrical impulses along the axon. So that's another thing that we'll end up seeing. And let's label them there. So this myelin is produced by specific cells, and we'll talk about those later on, but it really does serve a purpose. It really, the big purpose that we see most often that's going to be relevant to us is this speeding up the propagation of the electrical messages within the, or along the axon, so that we can get the messages moving faster. So that's something to keep on mind. And we'll have a look of those messages and how they pass along the axon in just a little bit. But let's finish off this little sketch that we've done of a neuron. And again, like I said, remember, some neurons will have myelin, some will not. Some diseases actually are associated with this myelin getting destroyed, like MS would be a good example. So that's something that we want to also keep on mind, that we need to learn normal anatomy, normal physiology before we can start unbundling the abnormal anatomy and physiology, which really are for your later courses, for your pathology classes. But I think that that's a really nice summary of key parts of a neuron. We'll also see neuron here on the bottom picture. And in fact, we can add to this bottom picture a little bit of a mechanism. Let me just jump out of here so that I'm not making our slide too messy. Let's do it this way. Ooh, I didn't mean to do that. Let's try sharing that again without that interference of my drawing on top of it. There we go. We can also see that we can measure that electrical current as it passes along the axon by placing an electrode inside the neuron's axon. This is a very fine tipped, typically glass electrode, and we compare the charge inside the nerve cell to the charge outside the cell, and we'll see that the nerve cells are negatively charged. The negative charging within the nerve cells is going to be important for us because it is this fluctuation in this charge. So there's going to be a quick spike to positive charge as the electrical current passes along the axon. So it will pass, and wherever it is, we'll see a positive charge inside the axon until it returns back to its negative resting charge. So that's how these electrical impulses are passing along the nerve cell's axon. What I wanted to do next, I think that, and we've already kind of looked at this a little bit, I wanted to talk next about what we call supporting cells, cells that help us. It's not just the neuron, it's not just the nerve cells, but in addition to that, we have various different kinds of helper cells that assist in nervous tissue. These could be physically helping, these could be physiologically helping, so supplying, for example, nutrients, energy, oxygen, removing waste products. They could be, like I said, physically adding structure, stability. So we have many different kinds of supporting cells. These supporting cells are known as neuroglia or glial cells. And let's have a look of the most important types of those. And the first neuroglial cells that I want to talk about are known as our astrocytes. The name really tells us a little bit about the cells. The name comes from the fact that these cells are often described as looking like stars. So they're these star-shaped cells that are supporting the nervous tissue, supporting the neurons that we'll end up finding. They're often responsible for things like metabolism of the cell, and they also can help with the many other processes within the nerve cells. But really important in supporting the nerve cells, ensuring that that we have those functioning in optimal condition and optimal environment. The second type of glial cell that I want to talk about, and give me a second, the name is a little longer, and I'm only a guy, so I have to take a little bit of time when I'm writing. I can't talk too much at the same time. So we're going to see oligodendrocytes. So oligodendrocytes are another type of glial cell, another type of supporting cell, play really important role in these functions of supporting the nervous system. And what's kind of interesting to me about oligodendrocytes is that they're really these cells that exist here on our diagram, if I can get the interference to stop. And they produce out from the cell itself this, I guess you could call it outgrowth. They produce myelin, and this myelin is actually growing around the axon of the nerve cell. So they're really important in that they help us to make the myelin so that we can then do those positive functions that myelin provided for us around the axon. So let's use a different color to highlight the cell proper itself. So this is the cell portion, and it produced this myelin that wrapped around the axon that we can see on that sketch as well. So these cells were our oligodendrocytes, responsible for that. Let's have a look of the next glial cell type. I think it's going to be worthwhile for us to add that to our list as well. And these are known as our microglia. And really, again, what we're seeing is that the name is kind of in the clue, or the clue is in the name. So microglia are very small glial cells They're often described when we describe them as this kind of spider-like cells in their appearance. They are phagocytes. And since they are phagocytes, what glial cells do, they help us with getting rid of any pathogens that might have gotten into the tissue. They engulf those foreign cells, break them apart inside the microglial cell, and then can eliminate those. So they're responsible for disposing materials. The final type of glial cell that I wanted to talk about is going to be our ependyma or ependymal cells. Both spellings are being used. And what ependymal cells do, let me just tidy up the writing so it's not as messy. Um, they are typically found really lining cavities within the body, especially cavities that relate to the nervous system. And they have these cilia, so these outgrowths from the cell membrane or cell surface as well. We, for example, see ependymal cells lining the spinal canal lining the ventricles of the brain. So they form these barriers, which then allows us to do things like have a blood-brain barrier, making sure that we're controlling what can pass to the nervous system. Nervous system is fairly easily injured, especially brain as an organ. So we want to regulate what gets there and what doesn't. So that's a function that we allocate for the ependymal cells. So now that we've talked about the nerve cell itself and we've talked about the supporting cells, I want to return back to this slide where we saw that we saw that nerve cell and neuron, and we saw that axon along which the electrical currents ran. And what I really want to do next is look at an individual changes in these electrical charges within the cell at one point in an axon over a time. So remember, these electrical impulses will spread through the axon. There will be a quick change to a positive charge, and then it turns back into its normal resting negative charge. We're focusing now on a single spot along the axon. So let's have a look what we can learn about that. This is really what it looks like. So at the rest, when nothing's happening, when the axon is just resting, the resting potential within the axon will be about negative 70 millivolts, so it's negatively charged. And then a stimulus takes place. This could be, for example, that action potential passing along the axon. The stimulus causes the inside of the nerve cell to become temporarily polarized. So what we normally did to establish this negative resting potential was really our sodium-potassium pumps playing role, ensuring that the inside of the cell is always charged with negative charges. But after the stimulus, during the process of depolarization, the inside of the nerve cell turns positive in terms of its charge. And this is really because the sodium channels open up and sodium rushes into the cell and changes the cell's inside charge into positive. So when we look at the word depolarization, you remember polar means opposites. And now we're depolarizing, so we're going away from opposites, so we're going close to zero. Sometimes we can overshoot that a little bit. So now the cells inside has reached a charge that's a little bit above the zero. What happens next is that this cannot stay like this for a long time. We have to start to normalize, return back to the normal stage, and repolarization takes place. During repolarization, the sodium channels close and potassium channels open. And as a result, we're now building negative charges inside the nerve cell. The membrane potential returns back to its resting potential, so repolarization is happening. What sometimes happens is that we actually go a little bit below that -70 resting potential. This stage is known as hyperpolarization, or it could be also referred as an overshoot. This is important because this really gives us a little period of time during which another action potential cannot pass. So it's known as our refractory period. So during this time, another action potential can't pass, so we don't get into that stage where the insides would be constantly positively charged. And then we return back to the resting potential. And again, remember, it was the sodium-potassium pumps that played really important role in ensuring that we maintained that -70 millivolts of a resting potential. And what we're going to see really is that these action potentials, these charges propagate along the action one after another. So we just looked at one spot in the action, but this positive charge changing from negative to positive charge will pass along the action throughout its entire length. And if we compare how the electrical impulse passed normally in an axon and compare it to when the axon is myelinated, we see that we can jump basically with that electrical current from one myelin shell to another. Between myelin shells, we have what's known as a myelin shell gap. So we jump that message from one myelin blob to another, which helps us to speed up the passage of the messages. So that's why myelinated axons are really good, really quick at passing messages. And this brings us to the very end of the, and I'm just trying to find my mouse, very end of the axon, so to the axon terminal. And we had a look of that earlier on. And what I thought that we could do here is really quickly sketch what does an action terminal look like and what does that space look like before we get to the next nerve cell. So let's see if I can draw this here. So this would be one single action terminal. So we see a little piece of the action there at the top of the screen, and then we come to that end of that action terminal, end of that neuron. So the message that we were talking about earlier on, it's going to be traveling as an electrical message, so as that action potential along this action. So the red arrow is going to be our message. And once this message reaches the action terminal, this is where we start the process of passing that message, not as an electrical current, but actually passing it as this chemical message to the next structure. So just to make our life a little bit easier, let's add the next structure here. In this case, I'm not going to specify whether it's going to be another neuron or whether it's going to be, for example, an effector. It could be that this is a muscle that we're seeing here, in which case this would be neuromuscular junction. But let's just imagine that it's another structure. It could be another nerve cell. And there's a small gap between these. So the electrical message just cannot jump over this small gap. Instead, something much more intricate needs to happen. To label our diagrams, what we're seeing here as part of the original neuron is going to be known as our presynaptic action terminal. So I don't know what I did there, writing. That should say presynaptic And then the opposite end is going to be our postsynaptic. Let's say that it's a new neuron. Let's see if I can fix this spelling error of mine. And in between of those, we do see that synapses, that's the term we use to describe this gap between the two. So synapses is this physical gap from one neuron to the next neuron. And how the message passed there, like I said, is going to be that it's going to be a chemical message rather than an electrical message. So as this electrical message reaches the presynaptic axon's axon terminal, that causes a vesicle to be released, and that vesicle then travels within the action terminal to the very surface of that action terminal. Inside that vesicle, we will actually hold chemicals. And now that this vesicle fuses with the surface of the action terminal, it's going to release these chemicals from inside it. And these chemicals will travel across the synapses or synaptic cleft, and they will eventually reach a receptor on the other side. This could be, for example, a protein where they bind. And as they bind into that receptor, that's going to cause that receptor then to it has to be a right match. So the chemical and the receptor need to be a match. But if it is, it causes the receptor then to cause some kind of a response on this postsynaptic cell. And that could be, for example, an electrical impulse that is then passed onwards, the message to within the next cell. So I hope that that helps you to kind of have a bit of a more of an idea what a synapsis would look like. We could make this prettier. We could color in with the same colors the presynaptic neuron so that we can see that it's this portion here. I'm getting a lot of interference. And it was within this neuron, this presynaptic neuron, that we saw these vesicles then traveling and eventually fusing to the outer wall of the vesicle, and in that way passing the message onwards. So that would be our presynaptic neuron, the axon terminal of a presynaptic neuron. Let's see if I can tidy up again the drawing a little bit. And then we had our postsynaptic neuron. That's going to be the where the message travels to. So that's going to be on the other side of that synaptic cleft or synapses that we saw between these two. So that's going to be located there. And let's just see if I can color it in. And you saw those vesicles within the presynaptic neuron's action terminal. And then remember that on this postsynaptic cell, we're going to then see those receptors on the surface. They're receiving those chemicals that were being released. And that was how we passed the message chemically from one cell to another. here's an actual picture of what a synapses looks like. It's not quite as pretty and quite as clear as the diagram that we just did, but I think it really clarifies that concept. So we see the presynaptic neuron, we see the synapses, and we see the postsynaptic neuron. So whereas it was electrical messages earlier on within the neuron, between the neurons, it was going to be chemical message. And here I have a little slide to really showcase and emphasize that point. We're seeing the synapses, we're seeing that that's responsible for passing that message in a chemical sense from one neuron to another, but it could be also from one neuron to, for example, an effector cell. We talked about the neuromuscular junction as an example, where a neuron joins to the muscle, sending that command for it to then act in response to that message. What we're seeing here is one diagram that's, I believe, from your textbook, a little tidier. We're seeing the electrical message coming in, that causing those vesicles that contain chemicals within the axon terminal, then eventually to fuse to the end of that. Those chemicals are released to the synapses and they bind to the receptors on the postsynaptic cell and cause the message to be passed onward. And that really brings us to the end of what I had planned to cover on this week's material. Like I said, I do have at the moment, I'm going to the school myself and I have a lot of homework. So I'm hoping that starting tomorrow, I'm able to share a little bit more on the announcements, for example, about the World Kindness Day and really World Kindness Week that we're celebrating on our campuses and opportunities there. As always, I appreciate you. I think that this class is really an outstanding group, and I feel very, very grateful to get to work with you each week as we're working through the material on this course. Until we see next time, that's going to be it from me for today. I look forward to seeing you in our virtual spaces, working together there and seeing where that journey takes us. As always, thank you for being part of this class, and let's make it another great week. Until then, next time, bye.